All right, so why did we take so much time doing Laplace transforms from unit step functions? Well, now we are going to be able to solve this monstrous differential equation, where on the left we have second order linear with constant coefficients, and then if that were 0, it would be homogeneous. But on the right, we have this weird step function. And remember, it looked like this, where this was 5 and 20 here, and then 1 was here. Would this ever show up, or are we just making up a crazy problem? Sure, it would. This looks like a harmonic oscillator with damping, right? So that would certainly show up. And then this is some weird driving force, where there's no driving force here. There's a constant driving force from time 5 to time 20, and then there's no driving force again here. So you might think of something oscillating, and then you're pushing on it for a little bit, and then you stop. And we want to think about what happens to the motion. So this can arise in real life. One option, you could do the method of undetermined coefficients. Almost. The problem is this, this function on the right is not continuous, but it is a constant on 3 different intervals. So what you would have to do is you would have to do 3 different intervals. And let's actually make this an initial value problem so we can talk through what would happen. You start with the interval from 0 to 5. So this is actually homogeneous, easy to solve. And then you get some curve, and then at the end of that curve, you'll get the initial conditions for the next problem. So, you know, whatever crazy curve you get at 5, whatever these values are of y of 5 and y prime of 5, you want your y and y prime to be continuous, basically. So then you use those values to determine the initial conditions for the next segment. And here it's going to be non-homogeneous, so you might need to do a little extra with a particular solution. Then you'll get some other unrelated curve, and then at 20, you're going to use the final value of that curve. So plug in 20, take the derivative, plug in 20. Then you'll get the initial values for the last problem, which is going to be homogeneous again. But it'll be different from the original one because you'll have different initial conditions. So you get a different solution. So you'll get 3 different curves pieced together. It will end up being continuous. And actually, you know, you look at this y double prime, your y prime, and your y, and you say, how could this possibly add up to this discontinuous function? Well, if you make your y and your y prime continuous, then it's the y double prime that has jump discontinuities. And that makes sense in the physics sense as well, because if you have a driving force, well, if you have no driving force at first, you just have some harmonic oscillator. You add a driving force, that's changing the acceleration. But now the force here is constant, so the acceleration is constant. And then you take it away, so the outside conditions are different, so you're changing the acceleration again. So the acceleration is discontinuous. The velocity can't really be discontinuous. You can't really be going from one speed to suddenly a different speed without going through all the speeds in between, as much as you would like to. And your position certainly can't be discontinuous. At least in our brand of physics, we can't teleport yet. So this all makes sense, and we'll glance at this again at the end when we look at the graph of this function. Okay, I'm actually going to stop the video here, and then in the next video we're going to solve this crazy differential equation.